both work as data scientists. They both work as data scientists at our local community college, at Salt Lake Community College, which serves just an enormous number of students in our community and contributes. I mean, I just am such a believer in the value of community colleges and what they offer. So it's really exciting that like our local community college has like a data science team to like make it more effective for our community. So I'm excited to. I'm always interested in hearing what kind of things you all are working on. So before joining Slick, Abby was an adjunct professor of linguistics, and that is Abby's background. And Keiko has a math background, and we're really lucky to have them both here speaking with us. So they are going to be speaking, as you can see here on this slide, about visualizing logistic regression results for non-technical audiences. I've been excited about this talk for a little while because I'm sure, like a lot of you all, this is literally something I've had to do and maybe done a not so good job, maybe done a slightly better job sometimes, but I'm just really excited for us to have this topic today because of how relevant it is to so many of us who are data practitioners. So Abby and Keiko, thank you so much for being here and for presenting to us today. If you have a question as we're going along, you can type it in the chat and there will be time at the end also for questions.
Thank you so much for having us. We're really pleased to be here. Yeah, Keiko and I are both, we're both at Salt Lake Community College, and we're very excited about this topic because this is also something that we regularly have to do as part of our jobs. And so we're excited to present sort of things we've tried and things we've learned.
All right, so without further ado, let's get started. Oh, hang on one sec. All right, so everything that we're going to present to you today, all of the code for the visuals that we're going to present, all of the slides, and Abby and I also created a little vignette. If you want to review that as we're giving the talk, or if you want to review any of the materials after the talk, feel free to go to my GitHub. All the stuff is there, and I believe the link will be posted in the Zoom chat. All right, so to begin, we're just going to do a quick little review of logistic regression. So logistic regression is used to model binary outcomes. And so what we mean when we say binary outcomes is there are two options for the outcome. So an example would be yes or no, 1 or 0. Some examples that Abby and I see here in the space of higher education is, did the student pass the class? So in this example, the binary outcome is either yes, the student passed the class, or no, they didn't. Another example is, did the student enroll for another term? The possible outcomes are yes, they enrolled for another term, no, they didn't. Another example, did the student graduate? Yes, they graduated, no, they didn't. So the design of the logistic regression is, right, we're trying to model this binary outcome, the outcome is discrete. But more than that, we're trying to model the probability that one of these outcomes happen. So, right, if we use the example of did the student graduate, we're trying to model the probability of the student graduating versus what's the probability that a student isn't going to graduate. And probabilities are continuous, right? They're bounded between 0 and 1. So how do we do that? How do we model this discrete outcome, but more than that, model the probability that one of these discrete outcomes happens? Well, we model the logit of the probability. And this is the equation for the logistic regression. And since this talk is about visualizations, I'm not like going to deep dive into the specifics of this equation, but just for your memory, here's the equation. All right, so what's the problem? Why is it so challenging, or why can it be so challenging to create a logistic regression and then present the model results to your stakeholder or your audience member who has no idea what the heck a logistic regression is, or even what a regression is? So the problem is stakeholders often want to know whether something affects an outcome and by how much. So an example here we might see at the college is, say there's a stakeholder and he creates a writing workshop, and he's interested in knowing whether his writing workshop increases the student's chances of passing, say, English 1010 with a C or above. First of all, that stakeholder is going to want to know, does the writing workshop have a positive, negative, or no effect? And if the effect is positive or negative, he's then going to want to know by how much. And that's kind of the key here, right? The stakeholder is going to want to know, yeah, my workshop, it increases the student's chances of passing English 1010 by 30%. But if you recall, right, with the logistic regression equation, we're not modeling probabilities directly, right? This is what we're modeling here. And so what that means is our model outputs are going to be in the log odds. And it wouldn't be an issue if, we knew if log odds were a measurement that we regularly used and everyone in the world was familiar with. But unfortunately, they're not. So that's one of the reasons it's difficult to convey the results. So, but right, we know probabilities. So what if we solve for P, right? And we can solve for P and we get this equation here. And we can plot P, but we still run into issues. And so, okay, so this plot, right, the y-axis is the probability, right? It's bounded between 0, 1, and then here's the x-axis, it's the betas, it's the equation for the line. What's important to note about this graph, right, is that it's creating a sigmoid shaped curve. And so what that means is that the slope of the curve isn't so steep, and then it gets steeper in the middle, and then the slope decreases again. And so what that means is the slope isn't, the probability isn't changing in a constant way. And I think we can see that more concretely if we look at a few example points. So if we look at a few example points where the slope of the curve isn't so steep, so say here, if we look at a 1 unit change, right, this is 1 unit, we're going from -3 to -2. And then if we look at the change in y here, right, it's not very big. We're roughly going from 0.07 to 0.12. So that's like a 0.05 change in probability. In contrast, if we look at somewhere a 1 unit change on the curve where the slope is much steeper, so say here, for example, right, this is still 1 unit change, this is also a 1 unit change, but now the change in y, right, the delta y is much larger here, right? We're going from roughly 0.5 to 0.75 change, so a 0.25 change in probability. And so that's why it's hard to convey just one number to your non-technical audience member, because really there isn't just one number to convey. The probability really depends on the qualities that the observation has. All right. So just a few preliminaries before we show you any visuals. So for all the visuals that we're going to show you here today, Abby simulated some data, and using that sample data set, she created a model. Like I said, all of this is in GitHub. So if you want to see the sample code or just the CSV file with the sample data set, feel free to look at my GitHub. So in our simulated data set, it describes students who took Balloon Animal Making 201 at University Imaginary. And these are all of the variables in that data set. So we have Mac user, possible responses, true, false, pet type, a student could have a dog, catfish, or no pet. And basically when we were creating the data set, we just wanted to make sure we had a good mix of variables. So, right, we have binary, categorical, continuous. If you're to import the data into R, and yeah, this is the CSV file if you're interested. This is kind of a snapshot of what the data would look like if you were to import it.
So we built a model from this data, and this is the same model that we're going to use throughout the rest of this presentation, where we're trying to predict whether the student passed the class on the basis of the other variables. A couple of quick data processing things that we did in order to fit the model are that we took the two continuous variables, we centered and standardized those, so prior GPA and height. And then for the categorical predictors, pet type and favorite color, we deliberately chose the reference levels for those categories. For pet type, that's no pet, and for favorite color, that is blue. So if you want to recreate the particular parameter values we got, that you would want to do that to the data set. So a quick summary of what this model looks like. We just used the good old LME4 package to fit a model. we see that we get, in fact, a few significant predictors of whether the student passed the class. Go to the next, we'll highlight the significant predictors that we see that students who wear glasses, students who have a higher prior GPA, and students who went to tutoring were more likely to pass this class, whereas students who have a dog or a fish, students who like green, and tall students were less likely to pass the class. I am 5'1", so that was fun. Quick disclaimer, some of the visualization options that we're going to present really strongly suggest a causal interpretation, right? That going to tutoring caused you to have be more likely to pass, or that having a dog caused you to struggle with passing. And we are not going to talk about whether that is appropriate, right? So there are, if you are interested in determining whether you can deduce causality from your model, that's a whole separate topic. Read Judea-Pearl, for example. We're just going to assume you have a model that you got somehow, and our question is just how are you going to present that model? So if you have a data set, if you have a model where you cannot justify a causal interpretation of some variable, then some of the visualizations we're going to present are not appropriate. So be wise. More generally, we're not going to talk about model selection and so on. We're going to assume that you got your model, you have a good model. What do you do with it next?
All right, just a few more preliminaries. So after creating the model, we created this data frame here, coefs.df. Basically what this does is it pulls the model coefficients, tidies them up, and puts them in one nice place. All the visuals that we're going to show you today are going to pull from this data frame. And here, we just pulled them out manually, but there are definitely packages out there. I think like Tidy Models can do this. So if you would prefer to do that, feel free to. So these are the colors that we used for all our visualizations. Since this talk is about visualizations, I just want to make a quick remark about colors. If you've been a data scientist, data analyst, or researcher for a while, you probably know that colors are important. For you newbies out there, yes, colors are important. Different colors can imply different things. I think, when we see colors like red or orange or yellow, we can implicitly think like, oh, that means like caution or warning or watch out. While colors like green and blue, they can mean colors like, good, this is okay. And so that's one thing to keep in mind. Another thing to keep in mind is the color palette that we chose today is colorblind friendly. If your audience member is colorblind, that's also something that you should definitely keep in mind. All right. Okay, now let's look at some visuals. So for this talk, Abby and I basically came up with 3 visualization families, and in each family we'll present at least 3 different visuals. And so for this first family, we'll be presenting model coefficients. I think from the perspective of like the researcher, data scientist, data analyst, this is probably the easiest thing that we could do, but as you'll see, maybe perhaps not the best thing for your non-technical audience member. All right, so I think oftentimes we see this a lot in like papers. So someone will create a model, they'll deem it's a good model, and then they'll take the parameter estimates that are spit out to them and plop it into a nice table like this. I think there's definitely a time and place for this, right? I think if your audience member knows exactly what a logistic regression is, this is completely fine. But if your audience member has no idea what a logistic regression is, they're going to be they might give you a reaction something like this, right? Because they're not going to know, right, what the heck is a parameter. They're not going to know what an estimate, standard error, z or p. They're probably not going to know what an intercept is. They're not going to know how to interpret these values and how these different values should be interpreted together. So if you have a non-technical audience member, we need to do better. So one of the things that we could do is we could create a caterpillar plot showing the change in log odds. And the way that we do that in R is, so we pull from that coefs.df data frame, which was storing all our parameters. We remove the intercept. We order each of the parameter estimates by sign and size. Then we added confidence intervals. We added a 95 and 50% confidence intervals. We did that by taking the parameter and then used the quantile norm function and multiplied it by the standard error. And then, of course, we used our handy ggplot for this plot. we use geom linear range size 1 for the 95% confidence intervals. So that's that long, thin band you'll see. For the 50% confidence interval, we use geom linear range size 2, and that's that thicker band that you see. And then for the median estimate, we just use geom point size 3. So, all right. So what's good about this graph? Well, first of all, it's clear which relationships are positive and which are negative. And the way that it does that is by first using colors, second by grouping those colors together, and then ordering the colors. What also makes this plot good is that it has a transparent relationship to the fitted model. So, right, there's not a whole lot we did here. We took the parameter estimates, we added some confidence intervals, and then we slapped it into this graph here. And you could argue that a table could do those things, right? A table can, you can color the cells of the table, you can group the cells and then order them, and you can also add like columns for the confidence intervals. So I think where the real beauty of this plot comes in is actually from the x-axis. So right, the problem with the table was there were just so many numbers that it was visually taxing. But with this caterpillar plot here, basically we've isolated all those numbers into one place here. So I think that's what makes this graph better than a table. Some cons are, yeah, the magnitude of effect is in the log odds scale. Like I mentioned earlier, right, log odds isn't a scale that most of us are familiar with. So your non-technical audience member might be asking questions like, what the heck is a 0.4 change in the log odds? Is the change between a 0.4 and 0.8 log odds big or small? And so all that they'll be able to get out of this figure here is that whether your parameter had a positive or negative effect or no effect. And as the researcher, data scientist, data analyst, it's your job to make sure that your audience knows what your graph is saying. So either you need to provide an explanation as to what the heck a log odds is in a tutorial on the inverse logit function, but they probably don't want to hear those things or learn about it, and you probably don't want to explain it. So we need to somehow do better.
So one option, and I've done this once or twice, but I consider this kind of a visualization of last resort, is what we call secret log odds. This graph is exactly the same as the graph that Keiko just showed, but we have relabeled the x-axis. So now instead of having numbers, it just says chance of passing is higher, lower, or the same. Next slide. Yeah. So the nice thing about this is it is very easy to do. The only thing we did was we relabeled the x-axis with words. And there is no chance that your audience is going to misinterpret the numbers because there aren't any numbers. So it's very easy to do. It's yeah. The problem, of course, with this is that we're not conveying the absolute magnitude of the effect, right? So we're saying, okay, which things are positive, which are negative, and which parameters have a larger coefficient than which other parameters. That's about it. Also, we aren't giving any numbers, but if your audience wants numbers, then this is a problem. So this plot is good in the very specific situation where your audience only in fact cares about the relative size of various effects and the sign of the effects, and where your audience really trusts you to be telling an accurate story. So in that limited situation, this might be a way to go, but it is usually at the bottom of my toolbox.
All right, so another option then is to present the change in odds ratio. So yeah, your audience might be more familiar with the odds part of log odds, right? I think from the context of gambling, we've heard odds before. And in the logistic regression equation, this is where the odds part is. And yeah, can't we just exponentiate to get the odds? Sure we can, and it's pretty simple. We get this equation here. And one thing to know about this equation is that the effect of the coefficient is now multiplicative and not additive. So that's going to come in. That's going to be important here in a second. So how we do this in R is basically everything is going to be the same, but right here, as you can see in the highlighted portion, we're exponentiating those odds, and then we added percents because we're comparing the change between two odds ratios. And Some pros for this graph is that, yeah, it might be easier to explain the odds than the change in log odds, right? We're more familiar with odds. It's still pretty easy. There's not a whole lot that we did different here, right? Basically, we just exponentiated to get rid of the log. Some cons, however, is that it's not the typical way we describe odds, right? Usually when we hear odds, we hear two integer values, right? The odds are for 3 to 1, right? Or the odds are against 2 to 4. But when you look at this caterpillar plot here, right, for each parameter, you're only seeing like one band, not two. And so you're going to have to do some explaining here. And the fact that you have to do some explaining might undo the benefit of using a familiar concept. Another thing to note here is that the exponentiated coefficients, yes, they're representing the changes in the odds, and that can be confusing. And another area that you should be aware of is, right, even though the x-axis clearly says this is a % change in odds ratio, your audience might be like, I don't really know what that means, but I do know what a % is, and oh my gosh, a prior GPA increase of 300% sure looks big and important. So so they might misinterpret this as probability. And so once again, we're pretty far removed from familiar scales. Another thing to be aware of is this change in log odds plot, the scale is symmetric, right? We're bounded between negative infinity and infinity. But what happens is when we exponentiate and we make the transformation, we're making that symmetrical scale asymmetrical, and we're now bounded between 0 and infinity. So what that means is basically everything to the left of the 0, that's going to be compressed on the % change in odds ratio plot. And everything to the right of 0 is going to be expanded. And that's going to be an issue because it's going to look like your positive effects are really big and your negative effects are really small. So examples are, if we look at prior GPA, right, the effect is positive. And it doesn't look like very large here, but if we look at the % change in odds ratio, it looks much larger. And then if we look at pet fish, where the effect is negative, it looks much smaller when we look at it in the % change in odds ratio plot.
All right, so the second family of visualizations tries to address this problem we keep running into, which is that with the raw coefficients of the fitted model, we're dealing with scales that your audience is probably not familiar with. So we thought, well, how can we work in a scale that your audience is comfortable with, namely probabilities? So as Keiko showed earlier, the problem with translating your model into probabilities is that if you're asking about what's the effect of a parameter in terms of change in percentage points, well, it depends on where you start. But of course, we could just choose a starting place and then express the change relative to that baseline, right? So if we can choose an appropriate baseline, we're basically computing marginal effects, right? But if there is one, then we can actually translate that model into probabilities that your stakeholder will be comfortable with. And in fact, oftentimes there are reasonable choices for what baseline you pick. One choice, and this is the one that we're going to work with today, is you could take the intercept of your model, say that's our baseline, and we're going to describe the effect of the predictors relative to the intercept of the model. You could also take your actual data set and say, okay, how many students in fact pass the class? That's our baseline. Let's describe things relative to that baseline. And if you fit your model in a certain way, which is in fact what we did, that can work out to being more or less similar to your model intercept. You could also say, well, our baseline is the observed success rate for a particular group. For example, if we want to look at the effect of tutoring, we might say, well, in our data set, what percentage of the untutored students passed? And then we're going to compare that to adding the effect of tutoring from our fitted model. Finally, it's possible that in your particular context, there might be some baseline percentage that's meaningful, right? So maybe your stakeholders happen to know that for balloon animal making 201, the typical pass rate in most years is about 85%. And so we want to use that as our meaningful baseline. Okay, so how do we do this? Well, okay, so we're going to do the intercept version today. So we just take our intercept parameter from our fitted model. We take the inverse logit. That gives us our baseline probability of passing this class. Okay, so that's probability number one. Probability number two is the probability of passing the class with some predictor, like if you got tutoring or if you wear glasses. And what we do to get that is we take our intercept, we add our predictor for that, we add our coefficient for that predictor, we take the inverse logit, there's our second probability. We can do the same thing with continuous predictors, although it's tricky there because a continuous predictor is not on-off, right? Wear glasses, you wear them or you don't, but prior GPA, it's not that you have it or you don't, it's that it's a particular quantity. But we can look at the change in probability for a particular change in prior GPA. So you pick a delta for that predictor that makes sense. For example, you might say, well, let's look at the change resulting from a change of 1 standard deviation in that particular predictor. Or you might pick something that's meaningful in context, right? So for prior GPA, we might say, well, let's look at the change in 1 point of the effect of a 1 point difference in your prior GPA. That makes sense for GPA. If you have, say, SAT scores, 1 point would not make a lot of sense, but 100 points might make sense in context. So once you've chosen a sensible delta for your continuous predictor, you take that delta, multiply it by the coefficient for that predictor, add that to the intercept, take the inverse logit, there's your probability. All these things give us point estimates, but if we want to get uncertainty, if we want to show a range of what we think the probability would be, we can get the endpoints of a confidence interval around that parameter. And then after that, we can take the inverse logit, and that gives us a range. All right, so the next slide shows an example of what this looks like. So we have done pretty much the same thing, except that for each parameter, we added that parameter to the intercept and then took the inverse logit. And so now we truly, for the first time, have an x-axis that is probabilities, which your stakeholders will be happy about. We're representing uncertainty in the parameters to get our confidence intervals. We're not representing uncertainty in the intercept, but of course you could do that as well if it's appropriate for a project. All right, so pros of this, well, yay, we have probabilities expressed as percentages. This is good. You're not going to have to do a lot of explaining about that. And the thing I particularly like about this is we're presenting two probabilities. We have this vertical line, which is the baseline probability of passing. And then for each predictor, we have, well, with that predictor, now what's your probability? And so now we're comparing two probabilities to each other. And I like this personally a lot better than describing a change in probability as percent change. It's commonly done, but I find that it's either misleading or not enough information, right? If you say this tutoring program increased students' probability of passing by 50%, does that mean that students went from 2% chance of passing to 3%? Or does it mean they went from 50% chance of passing to 75%? Both of those are 50% change, but those situations are very different, and your stakeholders probably care about the difference between those things. Disadvantage of this is, well, you do have to choose one baseline, and we're being transparent about the baseline we chose. But sometimes for some models, there actually is not a great choice for what baseline you use. Using the intercept in particular, as we have done, what that means is that we're showing as baseline or as normal students who are at the reference value for each of our categorical variables. So this is for a student who doesn't use a Mac, who doesn't wear glasses, whose favorite color is blue, and so on. In our example, that's kind of low stakes, but imagine if you had a categorical variable representing, for example, race and ethnicity, right? Then choosing your baseline character, your baseline category, and presenting that as normative could turn out to be very problematic. So doing this intercept approach is not appropriate for all kinds of data sets. And then because we chose one baseline, we're not showing the full range of possible effects at all baselines, right? We're just showing it for one particular baseline. Real quick, one variation on this kind of plot, if you really want to emphasize the direction of the effects, is instead of plotting dots and lines, we could replace those dots with arrows. So this graph here, this is the same thing, except instead of a dot, we've drawn an arrow where the base of the arrow is at that baseline, at that vertical line, and the head of the arrow goes to the point estimate. So we've given up showing the confidence interval, but now we're really emphasizing that prior GPA is good, that having a pet fish is bad. So the nice thing about this is it emphasizes the direction of the effect. One caution here, though, is that this graph has a particularly strong causal interpretation, right? We're really going to suggest to stakeholders that, tutoring brings you up, and that, having a pet fish really drags you down. And so if that interpretation is not appropriate for your data set, you probably don't want to do this. All right, so we said one of the big problems with this baseline approach is that we only chose one baseline. Well, we could try to deal with that by choosing more than one baseline, right? Why not choose several baselines and show all of them? So for example, what we might do this is we might say, okay, we've got this categorical variable, say pet type, right? Let's show a separate baseline for each level of that categorical variable. Let's show a separate baseline for dog owners and cat owners and fish owners and so on. So the way we do that is for one group, say dog owners, we take our intercept from the model, we add the effect of having a dog, we take the inverse logit, that's the baseline for dog owners. And then to get the probability of passing for dog owners plus some other predictor like tutoring, it's the intercept plus the effect of having a dog plus the effect of tutoring, inverse logit, there's our probability. So the next slide shows an example of what this looks like. This is the same kind of graph, except now we have 4 little plots instead of one big plot. And you can see particularly that the baseline for fish owners is lower than the baseline for dog owners. Other than that, it's pretty much the same thing. All right, so pros of this kind of approach. Well, okay, now we're really emphasizing to our stakeholders that the baseline is a choice and we could have chosen otherwise, and that the baseline matters. And now we're honoring the fact that these groups are somewhat different, right? So for example, for fish owners, the effect of prior GPA looks larger than it does for dog owners. And so now we're acknowledging that fact. In our particular model, the reason the effect is larger for fish owners is because fish owners start at that lower baseline, right, where the curve of the logistic where the logistic curve is really steep. But if your model had, say, an interaction between pet type and GPA, that of course you could just add that here too, and then you could. So this kind of graph easily also shows the effects of true interactions in your model. So it's really nice. And then we don't show this, but you could of course do the arrow version of this plot as well. Disadvantages of this approach is, well, we still have to choose one baseline for each group. And again, this is a low stakes example, but you could imagine situations where showing baselines by group might inappropriately suggest kind of an essentializing interpretation of groups, right? So if you're concerned, so if you believe that the lower baseline for fish owners is because having a fish is very difficult and you have to spend all your time taking care of the fish and therefore you have less time to study, that's one thing. But if you're concerned that you will show this to your stakeholders and they will say, oh man, fish owners are dumb, right? Then this would not be an appropriate interpretation, appropriate visualization to use. And then finally, it's kind of cluttered, right? We're adding more plots. It's not quite as clean as the single graph.
All right. So the big con that kept coming up, right, is that with the graphs that Abby just showed was, right, you had to choose a baseline. And I remember when I was doing this, I was getting frustrated about the fact that I had to choose. And frankly, I didn't even think about the intercept option. And so I thought, you know what, why don't I just show them all? And using R, that's actually not hard to do. And so it came right to the banana graphs. And so how this works is, say, for example, right, your stakeholder is interested in knowing how owning a pet fish affects your chances of passing balloon animal making 201. So what we're going to do is we're going to take all the students who don't own a pet fish, and they're going to be the baselines. And we're going to take their probability from 0% to 100%. And then for each probability, we're going to add the effect of having a pet fish. And so mathematically, that's what we're doing here. And how you do this in R is, so you have all the baselines here, right? We're going from 0.01 to 0.99. We don't go to 1 because of division by 0 issues. But then here is the, here we use the math equation that was on the previous slide, right? We take the inverse logit of the baseline plus the parameter estimate for owning a pet fish, and then the confidence interval. And you get this banana graph, and it's called a banana graph because it kind of looks like a banana. All right, so if you're looking at this graph and you're like, I'm not quite sure what this is telling me, I'm going to slowly go through the elements of this graph. So the x-axis is going to be the baseline probability. So this is a probability for all those students who don't own a pet fish. The y-axis is going to be the probability for all the students who do own a pet fish. So say, for example, we have some student and he has some qualities, whatever those may be, and he is predicted to pass balloon animal making at 25%. And we also know, though, one of these qualities is that he doesn't own a pet fish. If then we take a student who has the exact same qualities as a student who's predicted to pass at 25%, they have the exact same qualities, but now they do own a pet fish. So this is right, the y-axis value, then this is where they're going to end up, right? And I also included a black line that goes diagonally through the graph. This is the solid, this is the reference line. I like to call it the no effect line. So basically, if this banana curve ends up on the solid line, that means that owning a pet fish has no effect. And similarly, if the banana graph is over this reference line, it means that owning a pet fish has a positive effect. But here we see, right, the banana curve is under this reference line. So it means that owning a pet fish hurts your chances of passing balloon animal making. So kind of being aware that initially it might be hard to understand this graph. Well, I also just want to say, I think once you get this graph, you get it, and it's kind of hard to unsee. But how do we get the audience to understand what this graph is saying? I've presented banana graphs once in a report, and the way that I did it was basically I took one of the banana graphs, I isolated it from the others, because I think if on one page you have a bunch of plots that are confusing and hard to understand, it's just overwhelming, and I think your stakeholder might just like gloss over them. So being aware of that, I took one banana graph, I isolated on a page, I enlarged it. And then the second thing I did to help my stakeholder understand what this graph was saying was I chose one example point and I wrote some text as to exactly how he should be interpreting this one example point. So that's one way you can kind of overcome the difficulty of like explaining to your stakeholder the banana graph, is kind of using the layout to your advantage. All right. So, oh yeah, and also in R, you can facet wrap and show multiple banana plots together. So the pros of this graph is, yeah, you don't have to pick and choose a baseline. And because you don't have to pick and choose a baseline, you show the whole range of predicted probabilities. The cons are, however, it can take up a lot of space, and that's because for each parameter value, you can only show one banana graph. Also, as we kind of saw, it might be hard for them to initially understand. And another reason why this might be a con, a con for this graph is all the previous graphs we've seen, right? It was a caterpillar plot, and so all of the parameter estimates were in one place, and like you could visually compare them easily because they were all in one place. But now here, right, if you have a lot of variables that you're trying to show to your stakeholder, you have to create one of these for each variable. And so basically their eyes are going to have to like run across the page from plot to plot, and it might be harder to like compare and contrast them.
All right, third family of visualizations. Sometimes it might be the case that your stakeholders are not just interested in, percentage improvement, something like that. If, for example, if your stakeholders are trying to determine whether they should expand funding for a tutoring program, right, then your stakeholders might want to know, like, literally how many students did we help? Did we help 5 students? Did we help 500 students? That might matter. If your stakeholders are interested not just in does something have an effect, but how much, and if they're interested in numbers, then here's one way we could go about thinking of it. We could say, okay, in our particular data set, we had 2,571 students who went to tutoring. Out of those, 2,023 of them passed the class. Well, okay, suppose those 2,500 students had not been tutored. Well, in that case, how many students then do we think would have passed the class? Do we think, yeah, still about 2,000 would have passed the class anyway, which means tutoring didn't do much? Or do we think only 1,000 students would have passed the class, in which case tutoring was a huge benefit? So in other words, we're asking how many extra passes, like counts of actual students, I could shake the student's hand and say, congratulations. How many extra passing students did we get because of the tutoring? Well, we can use our model to try to estimate this. So to get a point estimate of this, how many extra passes we got, we can do this. We take all of our students who received tutoring, that subset of the data, we take that tutoring variable and we set it to false instead of true. So now we have a counterfactual data set. This is the data set where imagine they hadn't gotten tutored. We take that data set, we run it through our model, and now we've got counterfactual predictions of what would have happened if they had not been tutored. And then we just take those predictions and we sum up how many predicted passes we got. We compare that hypothetical sum to the number of actual passes we got, and there's our answer of how many extra passes we got because of tutoring. That gives us a point estimate. If we want to get confidence intervals, we can essentially take this, run this many times, 5,000 times or something, and each time take a slightly different draw of parameter values and get sort of a range of here's how many students we think passed because of the tutoring. All right, so here's an example of what that looks like. We have run 5,000 simulations, 5,000 counterfactual simulations of what if you hadn't been tutored. And on the right, we see a histogram of the number of extra passes in each of those simulations. And what we see is that it was probably somewhere between like 50 and 150 extra students. So probably not only two. Tutoring probably didn't hurt. We also probably didn't help 1,000 students, right? So the nice thing about this plot is that we're dealing with counts, and counts have a very straightforward interpretation that your stakeholders might really care about, right? We helped 100 students with this program. There's your answer. And we also have a really natural baseline, right? So we saw earlier that the effect of tutoring because of the baselines was different for fish owners versus dog owners. But also we had in our data set very few fish owners in the first place. So this is accounting for the fact that the effect may be different for different types of students, but also that you have more of some of these students than others. So essentially we're describing our actual population with this graph, which I like a lot. Disadvantage of this approach is that, in this particular graph, we have an axis labeled number of simulations. You might find that a little hard to explain to your stakeholder. And this graph also, it only works if the counterfactual makes sense, right? So a student who got tutoring, I can easily imagine a world where the student didn't get tutoring. That makes sense to ask. But suppose you were looking at favorite color, right? It makes a lot less sense to say, hey, student, your favorite color is blue. What if instead you liked green? What would the world be like? That seems it's a little harder to make sense of that kind of question. Finally, this graph has a very strong causal interpretation. We're pretty much saying right there on the graph, this is how many students passed because they got tutored. So if you have a data set where causal interpretation is not appropriate, then this is not the approach you want to take. We can do the same thing like with some of our previous graphs, and we can look at extra successes, not just for the whole population, but by group. And in fact, for this approach, it's particularly easy to do, right? So if your stakeholders care about dog owners and fish owners and so on, we can do exactly what we did before, but instead of summarizing for the whole data set, we just add up those extra passes by group. And this is an example of what that looks like. It's the same thing. We've just done it by group. In this graph, instead of showing histograms, we have flattened those histograms down into caterpillar plots. So now the dot shows the median simulated estimate, and then the lines show the range of simulations that we got. Advantages of this as well. First of all, I do like flattening the histograms because now we don't have a scale that says number of simulations and you don't have to explain what that means. The focus now is where it should be, which is on just what is our prediction and what's our range of uncertainty around that prediction. So now we're back to being able to show differences by group, which is very helpful. And again, if we had true interaction terms in our model, those would automatically be incorporated. When we run the data through the model, any interactions that are there are going to do their thing. Disadvantages of this is, well, in this particular visualization, we're not showing how these absolute numbers are related to the size of the group, right? So here it looks like, man, the tutoring was very helpful for students who don't have a pet, but did very little for students who have a fish. But in fact, we saw before that in terms of like percentage point gain, tutoring actually was more helpful for the fish owners. The reason it looks less helpful here is because there just weren't very many fish owners to be helped in the first place. And it's going to depend on your particular project, whether your audience cares about, percentage points, right? Are we helping this group a lot or little, or whether they care about counts, right? Well, okay, we care most about the big groups because we want the most bang for our buck, right? So sometimes your audience may say, we just want to help as many students as possible, so we're going to focus on the big groups. Sometimes your audience may say, well, there are these groups who we care about, and even if they're small, we want to make sure we are helping them also. So it depends on your context. Finally, there are things we can do to try to show not just number of successes, but group size. I'll do this real quick. In fact, let's go ahead and go to the next slide with the graph. Thanks. So here's one thing that we've tried to try to show both the size of the group and the size of the benefit. So here we've switched the direction of the counterfactual. Now we're saying start with the untutored students. Well, if we have tutored you, what could we have aspired to reach in terms of pass rates? The red diamond shows the number of passes we actually got. And then the black dots aligned show here's how many passes we could have gotten with tutoring. And so the nice thing about this graph is now we're actually seeing something about the size of the group. Now it's very obvious that the group with no pet is very large, the group with fish is very small. So it's putting those counts in context, which is helpful. The disadvantage, of course, is that if you have groups of very different sizes, the small groups are going to get squashed down at the bottom of the scale, and it's kind of hard to see whether fish owners were helped because so much of the real estate is taken up by the size of the non-group. So again, depending on what your stakeholders care about, you may want to show just counts or comparison to group size.
All right, so those are all the visuals that we have for you today. Some just concluding remarks is, yes, there's no right or wrong way, just better and worse ways for a particular project. So we hope that you'll get creative. And what visual is more or less appropriate really just depends on your stakeholder, what they're looking for, and the context and purpose of your research. We didn't go over this very explicitly, but use colors, the layout, and annotations to your advantage. I know in R, the ggplot has the annotate function, and with that, you can add text, you can add arrows, you can add shaded boxes, which can help enhance your visual. And then lastly, we hope you'll share your ideas with others. I'm kind of a newbie to this field. I've been doing this kind of work for about a year now, and this is something I really struggled with, and I couldn't find a lot of resources. It might just be because I'm new and I don't know where to look, but yeah, if you have a clever idea or unique idea on how to present logistic regression to non-technical audiences, I hope that you'll share it with the community. And with that, thank you so much.
Awesome. Thank you both so much. That was so fantastic. I personally have done kind of like everything you had in the first half, and then some of that I was like, oh, that's such a great idea, like using simulation and so interesting. That was really interesting to hear about. So if you have a question for Abby and Keiko, you can type it in the chat, or you can use the raise hand feature if it's going to be easier for you to say it, or you prefer that, and we can unmute you. I think there was one question earlier that just asked for a clarification about the pre-processing you did for the continuous variables.
Yeah.
I think you had it in the code, but if you just want to we what you did and why.
Yep. Yeah. So to standardize the continuous variables, we just we subtracted the mean and divided by the standard deviation. And we find that really helpful in general, because that means that then the intercept reflects a student with an average GPA as opposed to a student with a 0 GPA, which we hope there are many students like that.
Hopefully there's not a lot of those. Yep. Yeah, that it is real interesting. Like a linear model, you probably don't really need, for the model to actually work well, you don't need to scale it like you would for a neural network or a support vector machine or something like that. But it's that exactly what you said, that interpretation, how are you going to interpret and plot and visualize and summarize all that, the coefficients that come out. So I think that's that's actually a great question, and interesting to see how you might do some kind of pre-processing like that, even if it's not really required for the model to be able to converge or have sensible things at the answer. So that was a great question. So there's a question here that asked, is there a way to do like the banana graph for a continuous predictor, because the one you showed was like a person who had a characteristic versus not. So is there anything like that that you have tried to do or have done?
I personally haven't. I talked to Abby about this. I'm not quite sure, but maybe Abby, you do.
Well, so I think kind of like with the percentage point change, right? You can't show having a prior GPA or not, but you could choose, well, let's make the no effect line be for average GPA, and then the banana would be for like 1 point above average, something like that. So if you
Yeah.
choose an appropriate change in the continuous predictor, then you could do a banana for that. And you could even show several, like, here's the banana for a half point greater, here's the banana for a whole point greater, and so on. You could do something like that.
Yeah. What is, I was looking at those and I was like trying to mentally try to understand what the relationship between that graph was and a receiver operator characteristic curve. I was like, wait, is it the same? I was like, wait a minute, because we have the, like the one proportion on the bottom and one proportion. I was like, is this the same thing? I don't know. This is new to me, so I haven't thought deeply enough about it. Is there a relationship, like, or have you thought or looked at that at all?
I'm not sure, but like I totally thought of that too. I was like, oh,
Yeah.
this looks like an ROC curve.
Yeah.
But
Yeah, that'd be interesting to think about more. Because one of the things where I think it was interesting that you said, I tried to look for this and I didn't see a lot of resources and what does that mean and like how do I do this? The approaches that I have learned have almost all been through seeing what other coworkers are doing and or seeing like kind of in that sort of mentorship kind of situation, like, oh, that worked great. I'm going to start doing that. And a colleague that I worked with like a job ago, his name is David Robinson, and he would do this thing with the log or like the odds, I think, and make receiver operator characteristic curves for like without training a model. When I'm so used to thinking of it as like the outcome of a model, but just like looking at the odds differences. And so that's kind of why I was like, wait a minute. Is that the same? I need to like just concentrate for a minute and think about it if it's the same or not. It's interesting. All right. Are there any other questions? So there was just a question again about the continuous variable being standardized. So a unit change, once you standardize, a change of 1 unit means what? You're muted right now, Abby.
Yeah. Keiko, could you go to one of the first graph of the first caterpillar plot? Yeah. So so right there. So yeah, that's right. So 1 unit change now would be 1 standard deviation. And in fact, we put that in the label on this graph
Yeah.
because it's not obvious. Yeah. So so for prior GPA, 1 standard deviation turned out to be about 0.6. And
Yeah.
so we label that. And then also for height, 1 standard deviation turned out to be about 3 inches. And for this one, we thought that was, that makes about sense. 0.6. It's like a little more than half a letter grade. That seems reasonable. 3 inches. I know what that is. Yeah, but we certainly could have, for this caterpillar plot, we could have said, well, no, my stakeholders care about 1 point prior GPA. And so for that, we could have had the effect of 1. And so that would just mean the nice thing about standardizing and then using the standard deviation is we just added the coefficient right to the baseline. Or for this one, we even just use the raw coefficient. We could multiply the coefficient by whatever you need to get to the delta that you want.
Yeah. Nice. Nice. Any other questions from folks? Well, thanks so much for preparing this fantastic talk, for answering questions so clearly and so well. I think this is going to be a talk that people really use in their practical work. So I really thank you all for investing in this and making this. So let's say thank you. We can we can clap and celebrate and all those things. And again, thank you all so much for coming to this month's meeting of the Salt Lake R user group. If you are in Utah or the Salt Lake area, I encourage you to check out our in-person meeting that will be happening next October. It will be great to see some of you all and meet and say hello. And if you either way are here locally or far away, we encourage you to check out our November meetup when we will be back to this format, which we think works well for talks, which will involve Mark sharing about using Bitbucket with R. So thank you again so much for coming.